there exists E greater than 0 such that the map uh, phi, which is uh, R to Fe star R, sending 1 to Fe star of C. Yes. So this map is also called multiplication by left Fe star of C, which you can see why. Uh, so if you look at these two definitions, the definition of F split says that for just one particular value of C, which is the value which is the unit element, the Fe must, the Frobenius map should split. But this is, of course, strongly irregular. But for strongly irregular rings, you need for all C and R naught, which are elements not in the minimal points of R, you want the map to be there exists some E greater than 0 such that this map splits. And you can do this same trick, if you can call it that, with regard to F injectivity and F rationality. So, okay, let uh, Rm is if injective is the Frobenius map F from H I M R to H I M R is injective for all I. So this is something we saw before. And again, believe it or not, uh, so equivalently, Rm is F injective if there exists E greater than 0 such that the map Fe from H I M R to H I M of R is injective. Okay, so now you can see where I'm going with this. Rm is F rational for all C in R naught. There exists E greater than 0 such that the map, which we'll just call CFE from HIMR to HIMR from which is just multiplication, which is just multiplication by C and Frobenius. So this is injected. Here's where I should clarify something, which is that while this definition feels intuitive and feels like a general extension of what we require. This is not entirely correct. Uh, Rather, I should say it is incomplete, and R is co-Macaulay. So we do want this co-Macaulay definition in F rationality, which we don't particularly require for F injectivity. Okay. Uh, so those are,
Is it the case that F injective rings are Cohen-Macaulay?
oh no, no, no,
Oh,
no,
that's not true.
no, no. Yeah, of course, it doesn't have to be. Why? Uh, I'll, I'll come to that after defining or, or redefining all the terms so that like I have some, uh, I can do some stuff with that. Okay. So now R is weakly F regular if I star equal to I for all I in R. This is the symbol uh, which ideal. So and what is F regularity? R is F regular if W is weakly F regular multiplicatively close set W. And, okay. And so finally we can R is F pure if the Frobenius map R to F star R is a scalar morphism, which is that is for all R modules M, the map R tensor M to FE F star R tensor M tensoring over R. This is F tensor with identity injected. So yeah, I think I have defined everything that to be. Mm, mm, yeah. So now, what are the relations between these uh, rings, these type of rings? So again, uh, one very crucial definition: R is a finite if the Frobenius F from R to F star R is a finite morphism, or equivalently R is finitely generated as R power P mod. So Now let R be an finite ring. We have the following implications, and I will talk about them one by one and hopefully finish most of them by today and leave the rest sometime later. So regular implies only regular implies regular implies weekly regular implies fractional implies I need something for nonsense. CM plus normal plus product of domains. I guess normal rings are themselves product of domains, right? Should be.
Yeah.
So normal rings are themselves product of domains. So I think this is enough. Normal. And uh, this goes to the bottom line, which is uh, F split. This is if and only if F pure, which implies F injective, which implies reduced. And so this is the implication diagram as of now. There is another implication which I will draw in light blue color, which is true, but we won't see them today. Uh, so, right. So let's see these one by one. Regularity implies strongly if regular. I think Aditya, you already mentioned this. So he talked about how Frobenius uh, map is flat, therefore R is finitely generated as an R per P module, or rather, R is free as R per P module, or rather, you can look at F star R as free R module, and then you can then show that what do we want in strongly F regular. In strong F regular, for any given C in R naught, you need some E greater than 0 such that this map splits. But Frobenius is a flat map, therefore R to Fe star R, Fe star R is a free R module. So once we know that it is a free R module, you can extend this generator to a minimal basis for this Fe star R, and we can see that that gives us splitting. So regular implies strong wave regular is something we've already seen. Uh, what about strongly F regular implies F regular? So here's where we again use the fact. I think we already saw this something before. Strongly F regular is a local property. So okay, let me just write it. as a result. So theorem strongly if regular rings are f regular. All this under the assumption that R is a finite. So yes, let R be a strongly f regular ring. Enough to show that uh, I star equal to I for all I in R, since uh, strongly f regular is a local property. This is where we need the local property condition. So why is this enough? Because we have shown that R is weakly f regular with this statement. But then for every multiplicatively closed set of R, RW will also be weakly f regular. And that is the definition of f regularity, therefore R is f regular. So, so enough to do that I star is equal to I for all I in R. And this is also not very difficult. Let X be in I star, hence there exists C in R naught such that C x power P power E belongs to I P power E for all E large enough. Now we know that the map uh, phi, which is from R to Fe star R, which sends 1 to Fe star C splits. We know that for all E large enough, this map splits. So why is this useful? Well, note that. So the crucial part is that if you take the element X, where does it go? Let me call it E because this depends on E. So for all E greater than large enough, E of X is something like X dot Fe star C, because this is an R linear map, and so once you have defined where one goes to the some element, then you can immediately see where the other elements must go. So this is C x power P power E. What do we know about C x power P power E? This belongs to Fe star of I power P power E. But this is precisely equal to I dot Fe star R. Because yeah, once you take an element inside the Frobenius push forward, you have to raise it to the power of P power E, and so when you bring it out, it's just okay. So but there exists psi from Fe star R to R such that psi circle phi E is identity on R. Isn't that so? Hence, the element X, which is equal to psi E of phi E of X, belongs to I. Actually, yeah, this belongs to I since psi E of X belongs to I dot F C star R because map splits. So therefore, I star equal to I. We are done. So the only property that we have seen, so this sort of fits F regularity very nicely. So what do I mean by that? There is no uh, there is no property of strong F regularity which feels like overkill, you know, which doesn't feel like this is too strong of a condition. You may go with something weaker. It's not like regular rings. Regular rings are overpowered. So the Frobenius being flat is an overpowered condition. But here, if you look at this argument, it feels like we have used the property of strong F regularity to the utmost that it can offer. And we can't weaken this property of strong F regularity without, you know, without making this theorem false. So this is this is one reason why the conjecture still holds. So what do I mean by that conjecture? Um, so weak F, weakly F regular rings are strongly F regular. So it's a conjecture. It's not proved yet, and it's also not been disproved yet. But we have seen now that this implies this. This F regularity implies weak F regularity is obvious from the definition. So F regularity is strengthening of weak F regularity. So this part is clear. Actually, this whole part is clear. Now I have to show that weak F regularities are F rational, which I don't think I'll have time to do today. Um, we will see this part sometime in the next session. Strong F regular implies F split. That is also true from the definition because the equivalent condition R is F split if there exists E greater than 0 such that the map taking 1 to Fe star 1 splits. But strong F regularity says that for all C in R naught, the map taking 1 to Fe star C splits. In particular, if you put C equal to 1, you should be able to get that. You get the condition that 1 to Fe star 1 should split. That is the definition of F split. Therefore, strong F regularity implies split is clear. And F split implies if and only if F pure. Aditya, you talked about this, right?
I think yes, but not in much detail.
Okay. So yeah, this is I let me
But
see if I
maybe
can
you
do
can
it
leave it
now.
as an exercise or something.
Yeah, because it I think it uses Fedor's criterion. If I can uh just give me a moment, one second. Uh just put here. Mm, oh, you don't need Fedor's criterion. I'm sorry. Where is the- Okay. Yeah, I think it's not very difficult. I'll leave that as an exercise. So next theorem is uh, f finite plus okay. Theorem is that f split rings are f pure. Converse is true for f finite rings. So proof left as an existence. In particular, there exist rings which are f pure but not f split. So yeah, converse is only true if for f finite rings. So this part is done. This is also done. And f split implies if null if f pure is also done. And f rational if and only if f injective is also obvious from the definition. Let me go to the definition again. Yes, yeah. So f injective means that the local homology modules are injective, but for f rational, regularity is such a strong condition that even strong f regularity cannot uh, give you anything. So let's see these one by one. But before that, I have to point out something, which is uh, right, which is if you have seen this particular chart, you can see that regularity and all the strong F regular F rational, they lie between the regularity and Cohen tolerance. Okay, so you may ask something like, um, if you have, uh, are there any relations between these rings and the traditional? I wouldn't call it traditional, but the other set of implications that we have seen before. Regular implies complete intersections, implies Gorenstein, implies Von Macaulay. So, now are these particular rings, say Gorenstein or complete intersection, can we classify them in some way? The answer is unfortunately no. Uh, so, example number one, let what example should I give? Okay, let R be the polynomial ring k x y, and we need y sit kx, and f be x square. Then R mod fr is a complete intersection. But R mod fr is not reduced. Hence, R mod fr is not f blank. Fill in whatever you want, because if you look at this particular chain, all f singularities are reduced. Okay, so this whole thing, every arrow here leads to reduced, whether you go by this way or this way. So if a ring is not even reduced, then what are we doing here? So that is a very trivial example, but it just says why we can't compare these f singularities with the properties of it being complete intersection or Gorenstein. Uh, but what we can do is we can add on the condition of R being Gorenstein to some f singularity and see if that sort of gives you some converse or something. So this is example number one. And example number two is regular rings. We want strong if regular rings are not regular. And for that, uh, strong if regular rings are not regular. Okay. There should be an easy example here. Why am I struggling with this? Uh, right. So R, B, K, X, Y, modulo. What is the uh, what is the Veronese map here? K, X, Y, Z modulo X, Y minus Z square. So hmm, how should I convince you that it is strongly irregular but not regular? Of course, not regular is easy to see. We want to show that this is strongly irregular. Hmm.
Uh, I think we
Yeah.
discussed that direct summands of strongly F regular are strongly F regular.
Oh, yes, yes, yes. But okay, so uh-huh. Right. So um, did we also say that this is direct summand? I don't. Okay. Okay, fine. Maybe. Hmm. Yeah. So this is uh isomorphic to k s square st t square, which is inside k s comma t. Just uh, so my word that take me for my word that this k s square st t square is a direct summand of kst hence uh, is strongly irregular, but R R is isomorphic, but R is not regular. Why is it not regular? Because blank. Okay, so that is one example of strongly irregular rings which are not regular. And the middle three, this trio of rings, that is the conjecture. If you can give me an example, counter example to this, I'll be very grateful. So we don't have any example as of now. Uh, right. So, and then what about this part? Weakly irregular rings implies rational, right? So what about the convex? Uh, that is not very trivial. Mm, yeah, that is not very trivial, and I'm going to write that as some examples to cover in additional sessions. So there are some examples which uh, will be very nice to see, and the first of those is this example. Um, Let me write the title. So, F rational ring, which is not weakly F rational. So, Watanabe showed that um, R, which is FP T x t power 4, x inverse t power 4, and x minus 1 inverse t power 4. Uh, okay. Localized at M is an F rational ring, which is not F pure, hence not weakly F regular. Oh, okay. I think I forgot to mention one thing, which is that the conjecture is known to be true for uh, n graded rings over field. So this is by uh, Smith, Karen Smith. I don't remember the other author. Libesnik, I think.
Yeah, Lubeznik and Smith.
Libesnik, right? Yeah. Mm, Libesnik. Smith. Okay. So, okay. And that is one example which will be interesting. The second example is of course, F pure ring, which is not uh, F split, shown by that split thing with an example which will be interesting. And okay, and the third example is uh, which one? Okay, okay. So I'll fill this particular column later. Okay, so this is uh, this is the implication that we have now, and I have not filled all of them, but we'll do it in due time. Now I want to introduce another definition. Mm, the Frobenius closure of I is the set of all x in R such that x power p power e belongs to I power p power e for all e large enough. Here there is no mention of c. There should be some c in R naught because of course c must be 1 here. Instead of it being any element outside the minimal prime of R, here the c is 1. So this is the Frobenius closure of an ideal I. Uh, Note that therefore I is contained in IF, which is contained in I star, which is contained in I bar, which is contained in radical of I. Yes. So all of these are closures. This Frobenius closure, this is tight closure, this is integral closure, this is radical, all of them are closure operations. So, yeah. Okay, so for radical ideals, none of these are interesting. Uh, right. So, what do we want to say? Yes. Theorem. R is F pure if and only if every ideal is Frobenius closed. This is a nice theorem which I don't have time to prove now. We'll do it next time. This is sort of analogous to the F regularity that we have seen now and seen before. Weakly F regular if and only if every ideal is tightly closed. So now what does this theorem say? It says weakly F regular rings are F pure. This is because of this containment. If I equal to I star, then IF is sandwiched between I and I star, therefore IF must also be equal to I. Therefore, if every ideal is tightly closed, then every ideal is also Frobenius closed, which is therefore says that it's F-pure. So yeah, I did not. I said I will prove this next time, which technically, yeah, I'll prove this next time, but you can see why this containment now holds. Weakly if regular rings are F-pure. Uh, so the converse of this F injectivity not being F-pure, there is an example, it's slightly involved, which again, I don't have time now, we'll do it next time. Same with this part. But let me uh, copy this diagram. Okay, so this is the diagram that we have, right? Yeah. So this is Gorenstein. Gorenstein. So what this says is that F rational Gorenstein rings are strongly F regular, F injective Gorenstein rings are F split. And this is a very strong claim, but it is true. So, in a sense, the Gorensteinness sort of makes the top row the same and the bottom row the same. Can the top row and the bottom row, can you have some implication from this to this? F split to strongly F regular? Unfortunately, not. So, one example which I can give immediately is mm, yeah, one second. Yeah, okay. So, example, uh, let R be K XY modulo XY product. Then R is F split, but not F regular. I mean, strongly F regular. Okay, so let's see why this is the
But
case.
yeah, is this
Yeah.
Gorenstein?
Huh?
Is oh yeah, it's complete intersection. Sorry.
This is complete intersection, therefore it's Gorenstein.
Yes,
So
yes.
R is F split, but not uh, F regular. Okay. So why is that so? I think we have seen some example like this. Uh, okay. Bear with me for a moment. So K is FP. So take I to be, but not even F regular. Therefore, yeah, maybe not weakly. Take I to be the ideal X. Because of the principal ideals are tightly closed. What about X comma Y? take I to be ideal x comma y. Now we want to claim that,
This is prime, right?
oh yes. What about x square, y square, which is again x square comma y square. Is this I star, is I star equal to I? I'll leave that as an exercise. I can't immediately think the argument for that. Uh, okay. Maybe this is, I'll deal with this next time.
Maybe if you take x square or something.
But principal ideals are tightly close. So mm, ideal generated by one element, that's not very useful. In fact, principal ideals are normal.
No, maybe not, right? We saw some example where tight closure of y in the certain ring was x comma y, something like that.
Oh, okay. Just give me a moment. Well, mm, yeah, yeah, yeah. Yes, 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 yes. And where did I see this particular set? I for principal ideal. Oh, I star equal to I bar. Oh, yeah, yeah. I was confused. Okay. Okay. So let's take I to be x itself. Hmm. What about y? Y power, does y belong to I star? So hmm, what do you want to show? So you want to show that C y power p power e belongs to x power p power e for all uh, e large enough that there exists C in R naught. The minimal primes of this are x and y. So take C to be x plus y, which is not in the which belongs to R naught, and y. mm, yeah. So then x plus y times y. Uh, this belongs to, okay, this is actually equal to y square. In fact, y power
Uh,
d is y power d.
Maybe if we can show
Yeah.
x plus y lies in the tight closure, then
Ah, um, so how x plus y times x plus y power uh, p power e is x power p power e plus y power p power e. You want to show that this belongs to x power p power e?
oh, that's a equivalent problem anyway. So
Uh, you want to show this belongs to this ideal x power p power e comma xy. Uh,
some multiple of this maybe.
mm,
Maybe we can check later.
yeah, okay. Yeah, we'll do this tomorrow, next
Yeah,
time.
yeah, yeah.
Okay. So yeah, that is everything that I wanted to talk today. So this is the implication that we currently have.